Hey guys, Garrett here again, talking about our Chapter 32 intake and exhaust systems this week. Talked about our vacuum basics. Vacuum obviously referring to any pressure lower than atmospheric pressure. So whatever the pressure is, as long as it is lower than the pressure that we're in right now. So on that intake stroke, when the piston is moving downward, we're creating a vacuum source. So as long as it is a negative pressure, and that's where we're talking in our vacuum. It is expressed in inches of mercury, kilopascals or bars. We're seeing it more and more in that kilopascals. And why are we seeing it more in those kilopascals, guys? That's one thing to keep in mind. We're going to see that more and more versus just seeing inches of mercury. Why are we going to see those kilopascals more and more? Diagnosing and troubleshooting some of this with our vacuum. Vacuum problems can produce or contribute to the following symptoms here. We could have stalling problems. We could have poor starting, rough idle, poor acceleration, detonation or knock, and possibly poor fuel economy. Now looking at these, a lot of these could simply be attributed to maybe having a vacuum line disconnected. Maybe there was a vacuum line that is cracked, kinked, bent, something of that sort. So we need to be able to look over that, and this is where our visual inspection simply comes in, seeing what's going on with this vehicle by just simply popping the hood and looking at it. We don't have to get too far into a diagnostic sometime if we just simply visual inspect and see what's going on with that vehicle. We need to, like I said, inspect for improper routing. Maybe somebody else has been under here. Maybe there's been another technician or the customer's tried to fix some problems and improperly routed some of the vacuum lines. So something might not be connected to the correct place at the correct time where it needs to be. So you could have maybe something as far as an EGR solenoid that only has vacuum to it in certain amounts of time. That can't be connected up to our map sensor. So it can't be having that vacuum at wrong times. Simply disconnections, cuts, or kinks. Looking at something that's fell apart. We've talked about it with our GM models, such as the vacuum line that's directly onto the throttle body. Look at that. Make sure it's connected up properly. Make sure it's not cracked or cut by any means. And then wear near hot spots. We've also talked about this maybe on some of our late model Ford vehicles, where we see that vacuum line on the back side of the intake manifold or very far back there, where it's going to have a lot of hot heat back there. So in that case, we need to look at those plastic vacuum lines and make sure they're not melted. Make sure there's no vacuum leaking past that. One thing we talked about was making sure we use that smoke machine so we can see if we find any leaks. Very, very simple diagnostic. If we think there's any possibility of having smoke or having any leak anywhere, we could use our smoke machine to try to find any of those leaks. Talked about turbochargers this week. Turbocharger is an exhaust-driven air pump. Exhaust gases spin that turbine blade. That turbine itself is on that hot side, so that is the exhaust gas side. So you see up here where the exhaust gas is being expelled out of the engine, it comes down into our turbine housing here, and where it turns our turbine shaft. So we are seeing a turbine wheel and comes out and blows the exhaust gas back down to where it's expelled out the rest of the exhaust. Now adversely we had our cold side over here, that's our compressor side. So we had the compressor wheel and the compressor housing where it's directly forcing air back into the intake manifold now. So we're actually forcing air back into the intake. So we obviously have our shaft, our turbine shaft, that's connecting the two wheels together. So we can spin this turbine wheel, which is adversely going to spin the compressor wheel, therefore creating our boost pressure to blow back into that intake manifold. So we are having that extra increase of air so we can add that more fuel and we can have more power coming out of this engine. The turbine, as I said, turns the compressor wheel. The air is compressed and is sent to the cylinders from this. We use these on gas and diesel engines. As we talked about last week, we see this quite commonly on our diesel engines. Very, very common to see that. We are starting to see it more and more on our gasoline engines, however, also. Turbo lag. It's the lack of the immediate response. It's caused by the exhaust gas requiring time to build enough energy to spin the turbo fast enough to respond to the engine speed. It's something that we don't see with our superchargers, and the reason we're not seeing that with our superchargers is because they're driven by the belt, so it has power to it immediately at all times. However, with our turbo, we have little exhaust gas being expelled at maybe an idle or a low RPM, versus as the RPMs increase, in that case, we are going to have more, the turbocharger boost pressure is going to be able to raise as that RPM of the turbocharger increases. Our wastegate valve, excess output pressure can cause drivability concerns and engine damage. So if we had something, we can't have too much boost pressure now. We got to be able to regulate that back down. the wastegate allows a certain amount of exhaust gas to bypass the turbine wheel and when it reaches a certain level. That wastegate can be controlled by the PCM, or it can be controlled by manifold pressure. It has been controlled by manifold pressure for quite some time, except we're seeing it more and more PCM controlled, so we don't have those problems maybe with that cut or kinked vacuum line, and we can regulate stuff down now. If we had maybe a vehicle that needed to go into limp mode for some sort of reason, it can simply now open that wastegate up completely, and we don't have any boost pressure that can be created with this vehicle, versus if it was mechanically through that vacuum pressure, we can't actually stop it completely from having, from that turbocharger building boost pressure. So we're seeing a lot more of it being the PCM controlled. Here's a picture so you can see how the wastegate operation is actually working. So we have the exhaust gas being expelled out of that engine. Now we have exhaust gas going into the turbine housing and across the turbine wheel here. Now what we can do is, once this reaches X amount of RPM that it needs for the boost pressure being pushed out, what we will do is we'll open up the wastegate here. And we'll start leaking some of that exhaust gas past the wastegate. It still directs back into the exhaust, but it no longer goes past the turbine wheel. So that adversely, that wheel is not going to spin faster. So as more exhaust gas comes out, the further that this wastegate is going to open up. So as more pressure comes to this, it starts opening more and more and more and regulating the boost pressure that's going past this. So we see that to regulate the boost pressure so we don't have any internal damage to the engine. We don't have any problems with that at all. Superchargers. A supercharger is a positive displacement air pump, and it's driven by the crankshaft. They improve horsepower and torque by increasing the air pressure and density to the intake, a lot like our turbocharger is. Theoretically, we are once again just forcing air into the engine. The difference between this now, instead of it being exhaust driven, we see our supercharger here, where we have the supercharger maybe on this type where we set it on top of the intake manifold, but you can see that now it is not driven by the exhaust. We have a pulley right here. So this pulley, there will be a belt on this, and it'll be driven by the crankshaft. So it's actually driven the same as your guys' serpentine belt that the alternator or maybe the water pump is driven by. That belt is going to drive the supercharger, and adversely it's going to be able to turn the rotors inside here and create a force pushing down air once again into that intake manifold. The supercharger operation, air enters from a remote mounted air cleaner and airflow meter. Once it's past the throttle blades, air passes through an inlet plenum. The air is pressurized now by the spinning rotors, such as I had talked about. The heated air then passes, generally speaking, through some sort of intercooler, so we can have that air be dense as we can possibly get it inside of this engine. We want that air dense so we don't have high heat, and we're not adversely losing the power. If we have that very high heat of air, we're not going to get the power that we need out of it. We're going to have knock or detonation, ping. We don't want to see that type of problems with that. So a lot of times we'll see some sort of intercooler with that. It's not as common on our supercharger vehicles to see intercoolers as our turbocharged vehicles, but it is out there, and we do see these, and we're going to see more and more of them as the supercharger evolves. The supercharged system, I have two different types that we talked about, and it is our roots type and our centrifugal type. The picture I just showed you is a roots type. It uses a pair of 3 lobed rotor vanes. The belt is driving these via the crankshaft once again. So we have the rotors inside that are actually spinning, and kind of a lot like you guys maybe have a vacuum, where instead of having the vacuum source sucking in, we're actually pushing out, and we're sucking in from the intake side and pushing down, and now enforcing the air into the engine now. Adversely, we have a centrifugal design. The centrifugal design is very, very similar to our turbocharger, but it's not belt driven. But it's belt driven now. We have something now where the turbocharger is driven off of the exhaust. Now our centrifugal looks a lot like a turbocharger. We see the compressor wheel like we would see on a turbocharger, but instead of having a turbine wheel, we have a pulley. So that pulley is going to now go, and it's going to be driven by the belt or our crankshaft. It does spin the compressor wheel to build the boost pressure on this one. So these will look very, very similar maybe to your guys' turbocharger, except now it's still mounted maybe in the location where you would see an alternator or an AC compressor. So we're going to see it where the belt would actually be able to drive this. So either way, with each of these designs, we're talking a belt-driven design here. Either way, that is going to have that versus our exhaust-driven. That's where we're talking our turbocharged designs. maintenance for any of these pieces here. Normally superchargers have their own oil supply. Check and correct oil level periodically. It's one thing that a lot of people will sometimes miss. You may do an oil change. Well, the oil change just isn't an oil change. We need to be looking at that entire vehicle. We've talked about this. We need to be able to look at, maybe under the car. Look at the tie rods. Look at the steering rack. Look at everything under that car. Look for oil leaks. We're not just changing oil. And it goes with this too. If it has a supercharger, we need to look at its own oil supply. And there's regular intervals that's going to need to be changed. Has it been changed? We can ask the customer for that, or we can go back on our own data that we have in our system to see if that oil has been changed. It's something to check, just like checking our differential fluid. We check something like that if we're checking, maybe we're just checking any fluid in the vehicle, period. We need to be able to check this one also with that, and don't forget that one. Inspect for regular leaks, so if we notice a leak with it, we need to find out why it's leaking, where it's leaking, and fix that problem. And inspect for induction systems for leaks and filter condition. Leaks in a turbocharged or supercharged system are going to be a lot more prone than our naturally aspirated systems. And the reason behind that is we're actually forcing air now. So we might be able to, there might be vacuum lines that pop off. So we need to be able to look on each one of those and find, is there anything leaking with that. So we back all the way up into looking at those cuts, kinks, bends, stuff like that. We might have a turbocharger that's building too much pressure, or we might have a supercharger that isn't working properly. Maybe the actuator for the bypass actuator on it that we talked about previously in the week, it isn't working correctly. Well, we can look at that. The vacuum leaks for that also. And those supercharged and turbocharged vehicles are going to be a lot more prone to having those vacuum lines come off. Talking about our exhaust systems this week, so we talked all the way down from start to beginning, whether it be our exhaust manifolds, whether it was the exhaust itself, the catalytic converter, maybe it was the tailpipe, maybe it was the muffler. We talked about each one of those different pieces. We'll break that down just a little bit here. The exhaust manifold does collect and direct the gases, can be cast iron or stamped steel. We usually see it in those two things. Cast iron quite commonly because it's very easy. It's not expensive to make, where the stamped steel gets a little more expensive because we have to have more pieces to actually build that together. And we're going to see that stamped steel, or maybe we see something where it's stainless steel in more exotic or newer vehicle applications. We do not see anything aluminum at all on our exhaust manifold itself. The reason we're not seeing that on our exhaust manifold this time, it's just too much heat for that to be able to put out to it. We may see an intake manifold that is aluminum, but we do not see our exhaust manifolds as aluminum. They're designed for particular engine or chassis combinations. So we have an exhaust manifold that's not just made for just the engine, but also the chassis combination also. So we may see a Ford Crown Victoria engine that has a completely different exhaust manifold than a Ford F-150. We may see it as that's the same 5.4 maybe or 4.6 engine. It's the same engine. But just because it's the same engine doesn't necessarily mean that it's the same exhaust manifold. So make sure when we're switching that stuff, we got the exact vehicle to spec for that. The exhaust pipe and seals run between the exhaust manifold and catalytic converters. Exhaust gaskets or seals are used to prevent leaks between components. Most gaskets and seals are needed to replace if the exhaust pipe is being replaced. When you guys start looking at these right here, make sure you guys aren't using just that RTV gasket maker in there. We don't need to be gunking all that on. Put the correct gasket inside of that. If it needs a gasket or a seal, put that correct piece into it. We do not want to be putting the RTV sealant against it because it's going to be able to leak and blow past out. You guys can see the exhaust pipe here. Quite commonly in our area we see exhaust pipes such as we see right here. We're starting to rust up. Connections on it. If we're removing or doing anything with exhaust, it's something that we might need to use a torch on the stuff to break bolts loose. We need to get that heated up. So don't forget that. It's very, very tricky not to break these bolts onto exhaust. They've been rusted and they're thinned down now. So be careful when you are actually working with this exhaust in hopes that we don't break any bolts with that or break any of the pipe adversely also. Our catalytic converter